Past 1000 degrees, the bearings turn to liquid. This is the forensic autopsy of the 10 deadliest lubrication failures in heavy rail history. A 4,000 horsepower locomotive is a monster of friction. Thousands of pounds of steel spin at high speeds. The only thing stopping the engine from melting is a thin film of oil. It is thinner than a human hair. But machines do not just seize by accident. They are murdered by spreadsheets. When a dispatcher ignores a clogged oil filter to keep a train moving, the physics turn violent. The oil stops flowing, the temperature spikes, the heavy steel bearings start to glow red. Then they melt into a silver puddle. The engine does not just stop, it welds itself into a single block of scrap metal in a split second. How does a $20 maintenance shortcut turn solid steel into liquid? And what happens when corporate greed forces a multi-million-dollar engine to eat itself alive? In the 10th place, a $20 filter sat in its housing, months past replacement. The maintenance log reads oil black as tar. ISO particle count spike to 3 million per milliliter, silicon, sand, and metal shavings. The supervisor signs off to keep the train moving. That decision saves $20 on the spreadsheet. But with every mile, the filter clogs tighter. Oil pressure drops. Abrasive particles slip past, grinding into the hydrodynamic wedge. The oil film thins below 10 microns. Journal bearings shift from fluid separation to mixed contact. Steel meets babbitt metal. The first signs are subtle, a slight temperature rise, a faint vibration. But the oil is now a slurry of contaminants. The filter's rated capacity is overwhelmed. The crankshaft bearings are starved. The cost is a 3-day outage, $1.2 million in repairs, and a prime mover that could be replaced for $2 million. All for a filter that costs less than a tank of diesel. Deferred maintenance here is not an oversight. It is the opening act in mechanical murder. Number 9. The cold start fuel dilution seizure. Winter in the Canadian prairies. An EMD 645 engine sits overnight at 0 degrees Fahrenheit. The next morning, the starter cranks. 8% fuel and water have leaked into the crankcase, thinning the oil to the point of failure. The viscosity plummets. Hydrodynamic lubrication collapses before the engine even fires. Telemetry records oil pressure at just 2 pounds per square inch at crank-in, barely enough to wet the journals. The oil pump, starved of proper lubrication, grinds itself to death in under a minute. Gear teeth show adhesive wear, smeared babbitt metal, and streaks of copper. The repair bill is $85,000 for a full pump rebuild. If the engine had seized, the cost would have soared to $2.5 million for a replacement. This is not a slow decay, but a chemical ambush. The oil, once the lifeblood, turns to water under the wrong conditions. Deferred maintenance and ignored fuel leaks transform a routine cold start into a mechanical autopsy. 8th place. The oil pump drive gear, one hardened chunk of steel, becomes the single point of failure for a 500 megawatt turbine. When that gear fractures, it does not just slip a tooth, it detonates the lubrication system. Telemetry records the moment. Oil pressure free falls from nominal to 0 in under 3 seconds. The data trace is a cliff, not a slope. Torque spikes to 0.85 per unit just before the brake, a final scream of resistance as the gear teeth pit and shear under overload. The oil, once a clear river of protection, stops dead. Bearings lose their hydrodynamic wedge instantly. There is no warning, no time to react. Particle count in the sump explodes to 12 million per milliliter. Iron, silicon, and gear shavings flood the galleries. The engine's lifeblood turns to sludge. Bearings seize, journals score, and the crankcase locks solid. Downtime stretches for weeks. The repair bill hits $3 million. The root cause is a gear that cost less than $1,000, sacrificed to a maintenance schedule that ignored torque readings and rising particle counts. This is not gradual decay, it is mechanical decapitation. The moment the gear gives way, every safeguard collapses. Oil pressure drops to 0. Hydrodynamic lubrication is gone. What follows is pure thermal destruction. The bypass valve stuck open, a silent accomplice to mechanical homicide. When the filter reached its pressure limit, the control system should have forced a shutdown. Instead, the bypass spring fractured. Oil, unfiltered and loaded with abrasive grit, surged straight to the journal bearings during a high-load transient. The alarm log shows a differential pressure spike, but the warning was dismissed as a nuisance. Iron content in the oil reached 540 parts per million. Particle analysis found a surge at 45 microns, enough to bridge the oil film and grind the babbitt metal to paste. The pressure drop reached 15% below normal, but no one stopped the engine. The fractured spring photographed in the teardown tells the story, a 10-centimeter coil of cheap steel that failed by fatigue. While the suits tallied up the cost of downtime, the bearing suffered a slow, abrasive death. Hydrodynamic lubrication was stripped away, replaced by a slurry of metal and oil. The journal bearings never stood a chance. This was not a single-point failure, but a system-wide collapse, a chronic flaw that let abrasive contamination eat the heart out of $1 million prime mover. The cost of a new bypass valve was $45,000. The cost of a seized crankshaft and a melted bearing suite was nearly $2 million. This is what happens when management ignores the physics and lets a control system defect become a death sentence for the engine. Number 6. Contaminant abrasion through a failed seal is the silent killer of journal bearings. When a freight locomotive's bearing seal wears thin, it opens the door for sand and grit to invade the oil. Silicon spikes to 480 parts per million. The oil, once a clear barrier, becomes a slurry of abrasive particles, 2.3 million per milliliter. These fragments are harder than steel, grinding into the hydrodynamic wedge with every revolution. The oil film, already measured in microns, erodes down to the roughness of the metal itself. Third body wear takes over. The journal and babbitt metal are no longer separated by oil, but by a river of grinding sand. Vibration sensors pick up the first warning, a steady rise into the alarm band. The bearing temperature climbs past 140 degrees Celsius. On the thermograph, a cold spot turns white hot. This is the point of no return. The oil can't protect the metal. Friction climbs, heat rises, and the babbitt begins to soften. The cost of a new seal, a few $100s. The cost of a bearing suite destroyed by abrasive ingress, $120,000. The cost of a full power unit replacement, $2.6 million. Seal diagnostics and vibration analysis flagged the problem, but corporate deferred the downtime. The result is a textbook case of third body abrasion eroding the oil film, setting the stage for thermal destruction. What starts as a microscopic breach in a rubber seal ends with steel and babbitt on the edge of liquefaction. Number 5. Early. Babbitt. Liquefaction is the silent threshold where a journal bearing's fate is sealed, long before the metal melts outright. On the lab bench, a micrograph tells the story. The tin copper iron matrix of babbitt metal, once fine-grained and uniform, now shows coarse crystals and dissolved into metallics. This is not catastrophic destruction. This is phase change at the microscopic level. Under sustained heat, oil film temperatures holding above 150 degrees Celsius for hours, the babbitt alloy begins to soften. The grain boundaries blur. Energy dispersive X-ray scans reveal tin leaching into copper-rich pockets. The bearing's yield strength collapses. Viscosity readings from the used oil sample show a 30% drop after 1,500 hours of high-load operation. That loss alone is enough to thin the hydrodynamic wedge, pushing the journal into mixed lubrication territory. Once the babbitt softens, the metal can no longer support load. Friction climbs. Heat feeds on itself. Clearance vanishes as the shell deforms. The overhaul bill for this early-stage liquefaction is $220,000 for a bearing block rebuild. The prime mover itself, valued at over $3 million, sits on the edge of disaster. This is the metallurgical point of no return. The moment a maintenance shortcut, skipping an oil analysis or postponing a filter change, lets heat and contamination degrade the alloy, the bearing's fate is sealed. The suits may not see it, but the lab photo does. Once the babbitt grains coarsen, there is no going back. The engine is living on borrowed time. Number 4. Thermal expansion clearance loss is the silent assassin inside every overloaded prime mover. Under sustained load, the journal and the babbitt shell both grow. Steel at 12 microns per 10 degrees Celsius, babbitt at nearly 20 microns per 10 degrees Celsius. After hours at full throttle, the oil film temperature spikes past 160 degrees Celsius. A thermal camera shows a white hot crescent arcing across the bearing cap. The cap itself distorts, warping out of round as the metal creeps under pressure. That microscopic clearance, engineered to the last micron, shrinks by 30 microns or more. The eccentricity ratio climbs. The hydrodynamic wedge, already thin, is squeezed to the breaking point. TEHD models confirm the drop. A 30-micron reduction in clearance is enough to collapse the film from 10 microns to almost nothing. The oil cannot fill the gap. Mixed lubrication takes over. Metal asperities crash together. A bearing that once floated on a river of oil now grinds under dry friction. Every revolution ratchets the stakes higher. The bearing temperature soars, the oil chars, and the babbitt begins to soften. This is the moment where geometry betrays the machine. The clearance that protected the journal becomes a vice, setting the stage for catastrophic seizure. The next step is welding. Once the oil film is gone, there is no way back. The cost of ignoring thermal growth is measured in melted metal, seized cranks, and the total destruction of a $1 million engine. The suits may call it a design margin. On the shop floor, it is a death sentence written in clearance lost to heat. Number 3. Journal welding is the mechanical point of no return, a moment when a single bearing seizes and fuses a connecting rod to its crank journal. Hydrodynamic lubrication fails. The oil film collapses to zero. Steel and babbitt metal meet at full load, full speed. Contact pressure spikes. Surface asperities shred the last molecules of oil. Friction ignites a thermal runaway. Temperatures at the contact interface surge past 340 degrees Celsius in under a minute. Babbitt. Metal softens, then liquefies. The molten alloy flows into the microgrooves of the steel journal. Diffusion begins. Tin and copper migrate into the iron matrix, forming a new alloy at the boundary. Micrographs from forensic labs show a distinct weld bead, steel and babbitt fused, no separation, no hope of salvage. EDS mapping confirms a 5-micron diffusion zone, tin blending into steel, the fingerprint of adhesive seizure. The rod is now welded to the crank. The engine's heartbeat stops. The unbalanced load tears the crankcase apart with every attempted revolution. Vibration sensors spike. The repair bill explodes. Crankshaft replacement costs $2 million. Add in the labor, downtime, and a new bearing suite. The total loss climbs beyond $3 million, all triggered by a maintenance shortcut, a skipped oil change, a clogged filter, a dismissed vibration alarm. The evidence is permanent. Once a journal welds to its rod, the engine is condemned. This is not a gradual failure. It's a mechanical autopsy. The cost of prevention, a few $100s in oil and filters. The cost of ignoring the warning signs, total engine death. Management may argue about margins, but the weld bead on the crank tells the truth. There is no negotiating with molten metal. Number 2. Total bearing collapse. This is the moment when the engine's heart turns to liquid. Not a single journal, but 3, each one stripped of its hydrodynamic shield. The oil film, once a microscopic barrier, vanishes. Friction spikes. Heat builds with nowhere to go. The babbitt metal, a tin, copper, and iron alloy designed to flow under emergency, now melts outright. Cross-sections from the teardown show molten channels carved across the journal faces. The original grain structure is gone. What remains is a lumpy, silver-gray smear, tin, copper, and iron redeposited in streaks by the rotating shaft. Alloy spectroscopy confirms the worst. The babbitt has liquefied, then resolidified in a grotesque cast. 3 journals, all lost in a single thermal runaway. The lab's TEHD models tell the story in numbers. Oil film temperature climbs past 200 degrees Celsius. The pressure wedge collapses. Eccentricity ratio spikes. Viscosity falls off a cliff. Once the film drops below 5 microns, metal-to-metal contact is inevitable. Boundary layer friction feeds the fire. The bearing shell warps. Clearance is gone. The journals, once separated by a river of oil, now grind in a slurry of molten alloy and scorched lubricant. No oil, no life. The engine is dead before it explodes. The financial autopsy is as brutal as the metallurgical one. The suits saved a few hundred on skipped oil analyses and deferred filter changes. The result is an engine scrapped for parts, its value written off in the millions. The decision to defer maintenance is not a cost-saving measure, it is a death sentence. The evidence is permanent: molten channels in the journals, redeposited alloy, a prime mover that will never run again. The only thing left is the threat of what comes next. When the molten metal and oil vapor mix, the crankcase becomes a bomb. But even before the explosion, the engine is already beyond repair. This is the penultimate stage, total functional death, with the scars to prove it. And finally, in first place, the hot crankcase mist explosion. This is where every shortcut, every deferred oil change, and every ignored alarm comes home to roost. The physics are merciless. When hydrodynamic lubrication fails, a journal bearing becomes a furnace. The babbitt metal lining, designed to cushion steel at a few microns of separation, liquefies under boundary layer friction. Temperatures spike past 340 degrees Celsius. Molten babbitt splatters into the crankcase oil, vaporizing droplets into a dense mist. Each droplet, 3 to 10 microns wide, floats in the sealed chamber, invisible and deadly. Oil mist detectors, if they are installed and calibrated, register a rising fog. But in too many cases, the warning is bypassed, silenced, or never installed. The mist concentration climbs past 0.4% by volume. At this threshold, a single spark or a chunk of molten debris is all it takes. Ignition is instant. The crankcase becomes a bomb. Pressure sensors record a vertical spike, 5, 10, even 15 bars in under a second. The pressure wave rips through the engine block. Relief valves, if they exist, are overwhelmed. Bolts shear. Crankcase doors blow outward. Steel fragments become shrapnel. The engine is destroyed. Crew injuries are common. Fatalities are not rare. Sensor logs from documented events show the sequence. Oil mist climbs, temperature at the bearing shell surges, then a pressure curve that looks like a sledgehammer. Maintenance logs tell the other half of the story. A $20 filter marked overdue, a pressure sensor skipped for calibration, a $5 oil analysis crossed off the order sheet. The corporate spreadsheet records a tiny savings. The aftermath is a $4.2 million insurance payout, a regulatory fine, and months of litigation. This is not a random accident. It is a chain of decisions, each one shaving pennies from maintenance, each one ignoring the physics of oil and steel. The oil is the engine's lifeblood. When it turns to mist and the bearings turn to liquid, the result is total mechanical death, violent, final, and entirely preventable. The cost of prevention is simple: a filter, an oil sample, a sensor check. The cost of failure is a locomotive in pieces and lives shattered. The evidence is written in molten metal and pressure traces. The verdict is clear. Deferred maintenance is not thrift. It is criminal negligence, with the crankcase mist explosion as the final deadly proof. Across all 10 failures, one brutal pattern holds. When hydrodynamic lubrication fails, babbitt metal surrenders to thermal expansion and journal bearings liquefy. Every shortcut, whether oil dilution or deferred filter changes, turns a locomotive's lifeblood into poison. The cost is crankcase mist explosions and million-dollar wreckage, all to save pennies. The engine's death is never random. It is the direct result of management ignoring the machine's limits. Respect the oil or bury the engine.